We can do the same thing with some larger molecules. So here we're thinking about the dioxygen, and we'll also talk about superoxide and peroxide. And so in this case, we still have the combinations of the 1s orbitals. But now we're also adding in the combination of the 2s orbitals. So the 1s orbitals bond with the 1s orbitals, and the 2s orbitals bond with the 2s orbitals, because one of the requirements for making molecular orbitals is that orbitals have to have this similar energy in order to be able to overlap. They also have to have the same symmetry. And so in this case, a 1s orbital is completely symmetric, and a 2s orbital is completely symmetric, so those have the same symmetry and they can overlap. This top part here is showing the higher energy p orbitals. So these are the 2p orbitals from one oxygen atom and the 2p orbitals from another. And we see that the 2p orbitals, they can make combinations, make two different kinds of combinations that we're going to call sigma and pi. So when we imagine the 2p orbitals overlapping from the two different oxygen atoms where the shading is sort of the same, so that they're pointing at each other. So here's one oxygen atom, and here's the other oxygen atom. When they smush together, we get this sigma orbital. We can also imagine them, if they're not oriented in the same direction, so they're oriented like this instead, we can imagine getting this sigma star combination. And so on the molecular orbital diagram, this lowest one is the sigma, and the highest one is the sigma star. We can also imagine the orbitals overlapping side-on. So if we have our two oxygen atoms, but we're now looking, instead of the pz orbitals that are along the internuclear axis, we're instead looking at, say, the px or the py orbitals. And so if they overlap sort of sideways, like this, then we get this pi orbital. And likewise, we can make a pi star orbital by side-on overlap of orbitals that are shaded like this. So when they overlap, they constructively or deconstructively interfere, and there's no electron density, so we have a node there. So this would be the pi star orbital. If we look at sigma and pi, we see that sigma orbitals, they are symmetric about the bond axis, whereas pi orbitals, they have a node along the bonding axis. So because there are px orbitals and py orbitals that are degenerate, they're equal in energy, then we get 2 pi orbitals and 2 pi star orbitals. All right. And so we can see that the pi orbitals, their energy difference is less than that of the sigma orbitals. So the sigma is the top and the bottom, and then the pi's are in the middle. Because we get more overlap when the sigma orbitals overlap head-on, that means that that energy difference, the energy gained by bonding, is greater. So they're split more. The side-on overlap is more like a glancing blow. There's less overlap there, so the split isn't quite as big. We can fill up these electrons in the molecular orbital. So each oxygen has 8 total electrons. And so you don't have to do it this way, but I often imagine drawing them in on each side so I can keep track of them. So that's a total of 16 electrons but in the whole molecule. So if we fill them up from the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, we fill those one at a time. 13, 14, 15, 16. All right, now look, our highest occupied molecular orbital, often called our HOMO, is the pi star orbital. And we see that since those 2 pi star orbitals are degenerate, that we get 2 unpaired electrons. Sometimes we also care about the LUMO, the lowest unoccupied molecular orbital, and that in this case is the sigma star orbital.